All right, you ready? For some KCAT, KM, KCAT over KM. Okay, so we are still moving along in Chapter 7, looking at enzyme kinetics. So last time, we talked about Michaelis-Menten constant, Michaelis-Menten equation, Vmax and V0. So now, one of the other terms we're going to need to be able to define is KCAT. KCAT is defined as either the catalytic constant or the turnover number. It is referred to both. So KCAT equals catalytic constant equals the turnover number. And so from the other day, we had this. We had that equation, Vmax equals K2 times the total enzyme concentration. For a simple reaction, K2 equals KCAT. Now, which part of the reaction is K2 referring to? I'm sure you'd know all in just like 1 second. Good, that's K2. So for simple reactions, such as this one, this is a simple reaction, K2 equals the catalytic turnover number. So K2 refers to, or KCAT, refers to how fast, or the rate constant, of an enzyme after it's selected and bound its substrate. So it's a measure of once it has gotten to this transition state, how fast does it kick out the product? So it measures that. It also can refer to the number of catalytic cycles that each active site undergoes per unit time. So how fast does this active site reopen to be able to bind another substrate? So now knowing that K2 equals KCAT, we can rearrange this equation to define KCAT. KCAT is equal to the maximum velocity of the reaction divided by the total enzyme concentration. So if all of those things are true, looking at KCAT, which is over here, is K2. is KCAT a first or second order reaction? It is a first order reaction. How do we know it's first order? Right, it's only one reactant. So KCAT is a first order reaction. As such, it has units of inverse seconds. Any questions on that? That's just defining the term that we kind of already had defined earlier. Okay, in that case, let's look at how we measured the efficiency of the enzyme. So KCAT divided by Km is a measure of efficiency, which I'm going to define as enzyme effectiveness, which depends on the ability to bind substrates and rapidly convert to products. Yep. Yep, it's division. KCAT divided by Km is a measure of efficiency, which I'm going to define that way.
On the previous slide,
Yep.
you're saying that the number of catalytic cycles that each active site goes under
Yep.
is like how often it reopens to find a new substrate?
Mhm.
Is that, okay.
Yep. All right, so if we use the equation KCAT divided by Km to measure our efficiency, we can do the following to our Michaelis-Menten equation. So if we are at low substrate concentration, which let me refer back to my chart. Here we are at low substrate concentration, right? I'm towards the end of my reaction. What is happening to my concentration of enzyme substrate concentration after I pass the steady state? It is also decreasing. So at low substrate concentration, we are at very low concentration of enzyme substrate combinations. And the concentration of unbound enzyme is going to be equal to just about all the enzyme concentration that's in there, right? If I have very little of this, E total is this plus that. So if I don't have very much, then unbound E must equal about E total. So, looking at our Michaelis-Menten equation, if you want to spell out Michaelis-Menten, that's fine. I'm just doing a little shorthand. So using this information and combining that with the Michaelis-Menten equation, so in this denominator, I said if I'm at low substrate concentration, The denominator is going to be mostly defined by the Michaelis-Menten constant, because this is a small number. I can't eliminate it from the numerator because it's being multiplied by it, and so it's going to be close to 0, but if I multiply it by 0, it kills the entire numerator, so I'm just going to leave it up there. So I can rewrite this as so now I've defined my initial velocity in terms of K2 over Km times the concentration of both of these. Which, let's see if I can find some space to write on. Which means that V0 is directly proportional to K2 over Km at low substrate concentrations. Which is the rate of how fast that enzyme is turning over, or I don't want to use the word turn over because I already used it before. How effective this enzyme is at making products. If you don't have a lot of substrate, how efficient is it still at making the product? So we're kind of at the end, where before we were looking at excess substrate, now we're kind of at the end of the reaction, which is a better measure of its efficiency. So what are some things that could limit this enzyme efficiency? The rate's going to be limited by the fact that the enzyme has to float around in solution to find the substrate. What do we call that when two things have to float around to find each other? It starts with a D, if that's a help. Starts with a D, has two F's in it. Diffusion. Excellent. This is the diffusion-controlled limit. So the reaction can only take place as fast as it takes for the enzyme to float through solution, to diffuse through solution, to find the enzyme. So for most enzymes, this measure of efficiency, kcat divided by km, is on the order of 10 to the negative 8th inverse molar inverse seconds. If I have inverse molar inverse seconds as my units, Is that a first order or second order reaction? Second. Good to know also. As a second order measurement. Questions on my measure of efficiency? Maybe. All right. So then you may be thinking, how do we determine these values from experimental data? If you are in the biochemistry lab, you already know. Oh, yeah. Yep.
Is this just for
Yes. Still just for simple.
calling it a level?
Which we'll get to. We'll get to all the exceptions. Yeah. I think you guys sometimes ask leading questions because you know what's coming up next. Oh yeah, we're going to get to the exceptions, which will just be like there's 4 assumptions to get to the Michaelis-Menten equation. We're going to look at some of the assumptions that are not always true and how that affects the Michaelis-Menten equation. So, how do we find some of these important values, such as Vmax and Km? All right, so as we looked at, oh gosh, weeks ago it seems like now, high values of substrate, right, gets us something that looks like that. So at high concentrations of substrate, we asymptotically start to reach Vmax, which means we have this sort of curve, right, that speeds up and then levels off. Asymptotically means that it approaches but does not reach, if you haven't taken geometry in a long time. So high values of S lead to asymptotically, but I want to know what Vmax is. Numerically, I want to know it, and I can't find it from this type of curve. So we are going to replot the same data to get at Vmax, and right, and Km was here at 1/2 Vmax was Km. But if we don't know what Vmax is exactly, we can't make a good measurement of Km. So we're going to replot the data linearly to be able to pull out some of that information. So we are going to use the Line-Weaver-Brook plot, which is a double reciprocal plot. So before we had our Michaelis-Menten equation, that's where I just wrote down. All right, so there's a Michaelis-Menten equation. V0 equals Vmax times substrate concentration divided by Michaelis-Menten constant plus substrate concentration. I am now going to take the double reciprocal of this equation. Which now comes out to this form, 1 over initial velocity. Now I got Km over Vmax times 1 over substrate concentration plus 1 over Vmax. I have now written this in a way that my graph is now linear. So let's go ahead and plot that and see where these important things come out on my graph. so there's my graph. What am I going to put on my x-axis? This guy right here, this x, 1 over s. Sorry, x-axis. Inverse velocity is on the y-axis. So I got my y, got my x. Now that's my line of data. What value does the y-intercept tell me?
B.
Yes, b. b is this. So the y-intercept is 1 over b max. What about the slope? What does the slope tell me? Okay, let's do a little graph review. Okay, this is y-axis. This is slope. This is x-axis. This is y-intercept. That was not good, not good. It's all right. We're going to spend the rest of the chapter graphing stuff. So by the end of the chapter, hopefully, this goes a little smoother. All right, so the slope for this equation is going to be km over v max, which is useful, but actually the more interesting point on this graph is the x-intercept. Which is negative 1 over km. Which you could figure out if you set y equal to 0, everything else would shuffle out and you would get x to be 1 over km. So on this type of plot, I now have a numerical value for Vmax. I have a numerical value for km when I plot. So if I look at the graph above it, right, I'm now inverse 1 over s is still my x-axis. Inverse 1 over v0 is still my y-axis. Km is still on the x line, is still an x value, but now because I've inversed it, it's now on this side, 1 over and negative. And then my Vmax is still a y value, but now it's where x equals 0. So it's all the same information, it's just been pushed over to the side so that we can find it easily. This type of plot is the Line-Weaver-Burke plot. It is the most popular way to plot kinetic data. Not the only way, but definitely the most popular. Questions about my Line-Weaver-Burke plot? Yeah, Olivia.
Why is it called the double reciprocal or plot?
Because here I had V0 and S. Here I have 1 over V0, 1 over S.
Okay,
So both axes have been reciprocalized.
gotcha.
Where that is not true, like other types of plots, like the one I prefer is the Haynes-Wolff plot. That is a single reciprocal, because only the x-axis is 1 over. The other one is a different combination of things. So, yeah.
That's what I thought, so I thought we were taking reciprocal twice. Yeah.
Oh. Yeah, no, it means both axes have been inverted. Or reciprocalized, which will be my new, it's going to catch on, reciprocalized. If you say it enough, right, then it becomes part of pop culture. I think that's the rule. All right, so we had those 4 assumptions we had to make to get the Michaelis-Menten equation to work out. Here are my exceptions to those assumptions. So how this will play out like an exam is when you explain to me here is an assumption of Michaelis-Menten, except in cases like this. So they kind of work together. So you have to have 4 assumptions. There are going to be exceptions to each of those assumptions, so you'll have to know both parts of how they work together. So, a multi-substrate reaction. So our assumption was that we had this. We had one enzyme plus one substrate, making one combination, making one product, returning our original enzyme. That is an okay assumption, fairly good. A multi-substrate reaction in case the phrase multi-substrate isn't the key. It involves more than one substrate, so 2 or more, which turns out about half of all biochem reactions are multi-substrate. So an example that you are actually going to look at in a few weeks when we start looking at glycolysis. So we have fructose 6-phosphate plus in the presence of glyceraldehyde 3-phosphate, they combine with the enzyme transketolase, which, based on its name, which of the 6 categories of enzyme is that? It is a transferase. If it's a transferase, what is it going to do? What is it going to do? What will it do? Transfers a functional group. Correct. It's going to, especially, this is going to transfer a ketone functional group. They are the products. So you'll end up with ytterose 4-phosphate and xylulose 5-phosphate. You don't have to know the structures. ERY, therose, and XYU, lose. Kind of crazy looking. But I'll just show you when everybody's done writing, so we can see how it transferred that functional group. Just this is an example of one that we will look at more when we talk about a lot of carbohydrates. So here we have my fructose 6-phosphate. So fructose, and on the 6th position is my phosphate. Over here I have glyceraldehyde, and on the 3rd position I have the phosphate, so that's how it's named, glyceraldehyde 3-phosphate. In the presence of transketolase, I now, over here I had 1, 2, 3, 4, 5, 6 carbons in a phosphate. Now I only have 1, 2, 3, 4 carbons in a phosphate. So it has transferred this upper portion over here to the glyceraldehyde, because the glyceraldehyde was 3 carbons, now it's 5 carbons long. So it lopped off the top part, put it on the next one. So that's a transferase job, where it transfers a functional group. So, this is better written as enzyme plus 2 substrates. That's really a multi-step reaction because the enzyme's going to react with one of the substrates, pull off the carbonyl function, then the second one enters the active site, the first one leaves the active site, then it puts the functional group on the second one, and then they all leave. And so each substrate interacts with the enzyme with a unique Michaelis-Menten constant. So there's actually 2 Michaelis-Menten constants for this reaction, because I have to look at this reaction, and I also have to look at that reaction. So if there's, oh yeah,
Are we just assuming that it came with that?
we are making that assumption, yep.
So is there another exception to that assumption?
Yeah, but let me think. Yes, yeah, we'll do it in a second. Yeah, exceptions to exceptions. So there's going to be 2 Km values. If there's 2 Km values, there has to be 2 Kcat values, which means there's 2 Kcat over Km values. Yeah?
Will one of these substrates be more attractive than the other, so that it will grow definitely substrate 1?
Yes.
2, or will it trade off depending on which? it
There is
comes from?
usually an order that it has to bind, probably in this case, the fructose 6-phosphate first, so that it can pull off the functional group. Then that guy can float away, and the second one has to come in to put the functional group on. Because if it did it in reverse order, there's nothing to add to the second substrate. We have to take something off the first one, put on the second one. So, which is why I'm drawing it as single arrows, because once you've pulled it off, it's unlikely to put it back on to. Good on that. Okay, let's do the other 2 exceptions. This is my exception to the previous one. So, multi-step reactions. A multi-step may only have one substrate, so the difference is multi-substrate, many substrates. This is usually one substrate but many intermediates that are in equilibrium. So this would be something more like so it is one substrate reacting, but every single step is in equilibrium. So there is no definitive last step. What would force the product to be made is that the subsequent step, so if this was like the citric acid cycle, the next step in the cycle would need that product, and it would force Le Chatelier's it all to product because it needs it in the next reaction. So we will look at some of these in the citric acid and glycolysis where they all the steps are in equilibrium, but because you're going to need this product for the next thing you do, it's going to force it to make the product. Yeah?
Why are we not assuming that the last step goes into the
Because it's the exception. Because I guess as an assumption goes to last product, this would be the reason that it may not go to all one direction.
Can you say that again? Why?
So our assumption was we can only make product in our last step. This is the exception to why the assumption is not always true.
Because it needs it.
Yep. You have a question, Rachel?
Yeah, that's the.
Okay, perfect.
Worked out.
Good. So what this means for our exceptions, that Kcat is only equal to K2 in very simple reactions. Kcat is still the catalytic turnover number. It still tells you the likelihood of making this, how fast it turns it over. But in cases like this, Kcat is not just equal to K3. It's actually going to be a combination of rate constants that is beyond the scope of that discussion. Just know that Kcat doesn't always equal K2.
Is it possible to calculate that?
It is. It is. You would have to mess with the concentrations to figure out which one is actually the true intermediate. And then, yes, the answer's short. Short answer, yes, you can. You'd have to experimentally mess around with your reaction a lot. Yeah.
How is there a one substrate, but there's A, B, and C?
Because it's I'm just showing it as a transition state to kind of distinguish them. Because if I had A double dagger, P plus E, that may be confusing. Apparently this is equally confusing. A plus E makes this new combination where B is an intermediate. It's not all the way to P yet, it's somewhere in between. So then B goes through another semi-reaction to get to step C, which then goes through another equilibrium step to get to E. So if you're looking at it'd be like, right, if this is my A, that's my P, I have to go through B, C. I draw too many lumps, but one too many. Yeah, there we go. Yeah.
So you don't have to introduce a new substrate or enzyme?
Yeah. The idea that P is being used for something else should keep forcing it to be spontaneous. Are we all ready for the third exception? Non-hyperbolic reactions. So many enzymes have more than one active site. So it's not just the traditional Pac-Man that you think of when you think of an enzyme. Most enzymes have more than one active site. If they do, it does not obey simple Michaelis-Menten kinetics. Because again, our assumption is one substrate into one active site of one enzyme goes through one change to make product. So if it has multiple active sites, it can no longer obey Michaelis-Menten kinetics. Why, you might be thinking, is that true? Mm-hmm. So the presence of a substrate at one active site can, most likely will, affect the other active sites. So what protein, I wouldn't necessarily call it an enzyme, have we seen where the presence of a substrate at one site affects the other three sites? Hemoglobin would be an example. It's not exactly an enzyme, but when one oxygen binds, it forcibly changes the structure of the whole protein to then be ready to accept other oxygens. We will see this in some of the glycolysis enzymes, that you have to both have the sugar enter and a phosphate group come from the other side to allow the reaction to take place. And so there's going to be several enzymes that we look at that has two active sites, both of which have to be active to make the product. So, non-hyperbolic reactions are ones that, they don't have the nice little, doesn't have that kind of picture. It's V0 versus S curve would be different because you're actually looking at two things. So, good on that? Assad. How about we stop there? I let you go 10 minutes early. Because the next section is, if I start it, I'll want to finish it, and really it's a discussion for inhibition, everything that inhibits enzymes. So we will save all the graphing palooza for Friday. Yes, there'll be a group quiz.